Okay, so we continue about strontium titanate.
This looks different.
The importance of oxygen vacancy.
Ah, okay.
Okay. Thank you. Good afternoon. I come from Metz in Lorraine, in the northeast of France, and I will speak about oxygen vacancies, and especially about the possibility of detection of oxygen vacancy in strontium titanate by Raman spectroscopy. So, 3 keywords in my talk: strontium titanate, example of antiferrodistorsive phase transition and quantum ferroelectric; oxygen vacancies, which are very important for application concerning, especially for electrochemical and electrical damage. It's also important for doped strontium titanate, as we have seen just two talks before. And Raman spectroscopy, which is an efficient tool to study phase transition. So the main question of my talk is Raman spectroscopy able to probe oxygen vacancies? 10 years ago, Tene and co-workers have investigated the effect of reduction of the Raman spectra on strontium titanate. They found new lines which are indicated by red square, and they attributed these new lines in the Raman spectrum to oxygen vacancies. But we have noted that these lines are located at the same, nearly the same position as in the iron doped sample. And is the case for in the thin films, single crystal or nanocrystal. So that means that probably these new lines could be attributed to iron and oxygen vacancy pair. So is the reason that we have decided to reinvestigate by Raman spectroscopy the question of oxygen vacancy in strontium titanate. For this, we use 2 samples, one untreated sample and one reduced sample. And for the reduction at a high temperature on the argon atmosphere, and we have estimated the deficiency of oxygen to 0.5%. So which is important in our studies that we use the same source of material for 2 samples in order to avoid any contamination by impurities, particularly for iron. So we investigate by Raman spectroscopy with exciting laser at 633 nanometer, and we make measurements on cooling from room temperature down to 93K, so just below antiferroelectric transition. Also, in order to corroborate our results, we applied principal component analysis. It's a statistical method used to classify data. So first, I show you the results obtained in untreated samples. So the Raman spectrum is relatively complicated, and you see here the evolution with temperature. We can see the peaks labeled 1, 2, 3, and so on, which are well known and attributed to second order scattering, and the R lines, which are seen in the lowest, in the low temperature, are due to antiferrodistorsive phase transition. I remind you that in principle, first order Raman scattering is forbidden in the cubic phase. So we have no additional line. It means that it's the proof that we have a stoichiometric undoped crystal. Now we go to the comparison between untreated and reduced sample for the same temperature below AFD transition. So we observe the same peak in both samples, but additionally for the reduced sample, we see new lines noted A, B, and C. We can point it out that our spectrum is completely different from this reported by Tene and co-workers 10 years ago. If we look at the temperature dependence of the Raman spectrum in the reduced sample, the new lines A, B, and C increase in intensity on cooling. But the position is relatively constant as a function of temperature. So we have detected 3 new lines, A, B, and C, and these lines are enhanced by reduction, treatment, and cooling. The question is how to distinguish the own effect of reduction, so that means occurrence of oxidation vacancy, from the effect of the temperature on the Raman spectrum. For this, we use principal component analysis. It's a statistical method which can provide the relative change of a spectrum compared with the mean spectrum, if you make an average of all spectra or all data. So that means that the spectrum can be expressed as a function of the average mean spectrum and as a function of principal components. And principal components give idea about the variability of a special spectrum. Here, S1 or S2 are the contribution of the spectrum to each principal component. S is are called score or weight of the principal component. So I can show you the results with this analysis. We took all data, so that means untreated and treated samples, and what we observe, you can look at this 2D picture. The mean spectrum is at the origin. Here you have on the upper part the spectra or the data corresponding to the reduced sample. And in the lower part, all data corresponding to the untreated. So you have a clear separation between both series of data. Another important point that if you look at, for each series of data, if you look at the temperature change, you can see that you have from the right to the left a decreasing of the temperature concerning the data. That means that if you look at principal component number 1 or number 2, the number 1 it corresponds to the effect of the temperature for both samples. And concerning PC2, principal component number 2, is the effect of the reduction of the treatment. And you can see that the reduction gives a more effect if you are at low temperature. So we have a clear separation about the effect of temperature and the effect of the reduction by this analysis. Now, if you look at the loadings, so we can see here on the upper part, the experimental data at low temperature. And here, the loadings for PC1 and PC2. In PC1, you have, I remind you, is the effect of temperature. And you have the part here, the part of the spectrum, which is particularly sensitive to the temperature. And here you see is due to the second order scattering, if you come back to the Raman scattering. If you look at PC2 is the effect of reduction. So these peaks in red corresponds to the part of the spectrum which are affected by the reduction. And you can see that these ranges nearly corresponds to the new lines A, B, and C derived from the comparison between untreated and reduced sample. So that means that we have shown by means of the comparison and principal component analysis that the new lines A, B, and C are related to oxygen vacancy. Now the question is, which is the real origin of these new lines? Because I remind you that, in principle, in the cubic phase, no first-order Raman scattering is expected. First observation that these lines are located at the same position as optical phonon deduced by hyper-Raman data in the cubic phase. So that means that these lines correspond to first-order lines of the stoichiometric lattice. And these lines are, in fact, activated by local symmetric breaking due to oxygen vacancy. So, the effect cause local polar regions with diameter called L here. So this cluster or polar region have a tetragonal symmetry. So that means that you have a breaking of Raman selection rules, which can induce the observation of first-order lines. Another important point is that this cluster around oxygen vacancies are also responsible for the asymmetry of some lines. I will show you how in a few. Due to the local symmetry breakdown, not only the optical phonon at the Wilwin zone center can be activated by defect. Here you have the frequency as a function of the wave vector. Here, the zone boundary. So you can, due to the defect, you can see by Raman phonons with different wave vector. And we can use for the model initially proposed by Richter concerning the intensity of first-order Raman line. This model is more and more used now for nanostructure. Here you have a Gaussian distribution which depends on the dimension of the nanocrystal or the cluster. A is the lattice parameter. Gamma is the line width for stoichiometric material, and omega q is the phonon dispersion. And you make a summation on q star. Q star is the reduced wave vector. It means in units p over a lattice parameter. So if you have large L, means you have no defect, you find again the Lorentzian shape. So which are the results with the model? It's shown here. So you have here the experimental data, and we look at this line, A line, and we make calculation with L1 equal to 20 lattice parameters. So that means that you have nearly stoichiometric crystal. In this case, you have the red line shape, so a symmetric line. By contrast, if you use L2 equal 4A, that means that you have many defects, many oxygen vacancies in your lattice. With the calculation, we obtain the blue shape, and you see that the position, maximum position, is nearly the same, but you have a broadening on the upper part of this line. So that means that the asymmetric line shape of this line is due to cluster around oxygen vacancy, and also due to the relaxation of Raman selection rules. So I go to the conclusion and summary. So the main question I have is Raman spectroscopy able to detect oxygen vacancies in social tantalite? I can answer yes, we can do it, and with a relatively good sensitivity, because we detect 0.5%, the effect or the influence on 0.5 deficiency of oxygen, 0.5%, of course. But it's necessary to check if you have no other source of point defect of impurity, because this kind of defect can give rise to the same induced line. And we have seen these oxygen vacancies by activation of phonons on the win-win zone, and not only to the at Q equals 0. For the next future, we want to confirm our model concerning the link between the cluster size and the oxygen vacancy concentration by measuring the different reduction ratio, and to look at the degree of asymmetry we can obtain by Raman spectroscopy. Okay.
Thank you
for your
much.
attention.
Thank you very much, and the paper is open to questions. Yes, please.
Without microphone.
Okay.
Closer. Yeah.
So first question, these were single crystals.
You should.
These were single crystals you studied. Single crystals.
Yeah.
Okay. So my question will be, can you measure do similar things on polycrystalline samples? Can you measure this Raman spectra, similar Raman spectra on polycrystalline samples?
Yeah, of course.
So you get the same results?
Additional lines due to grain, because grain creates some stresses and so on. And if you have stress, strain is something like defect, so it means that you have a breakdown of Raman selection rule, and you can have additional lines, so it's more complicated.
Of course, strontium titanate was studied many times as a function of oxygen content with respect to conductivity and other properties. So are these samples transparent, or they are black after reduction? So you didn't measure conductivity, but apparently they are very good conducting materials.
Yes, another question?
Yes, did you verify that the first two principles? Did you verify that the first two principal components explain most of the variance, and did you look at the patterns for the other components to see if there was any hidden features? Like component 3, because maybe it would reveal more features.
It's ready?
Or maybe it would be mostly noisy, I Like, why did you limit to 2 principal components? Yeah, you can, analysis will give you many. Okay, so it does explain most of the variance.
Any more comments? And yeah, very short. One of you only, and without micro, I understand. Yeah.
Just
Without micro is a problem.
Point defects due to
We have to move to the next talk. I'm sorry, but he's in charge of that. So thank you again very much. We come now to the talk, which is not on strontium titanate, but on aluminum oxide and on cation substitution effects in ferroelectric type oxides. Thank you. Please.
Thank you, Chairman. I'm Ito from Tokyo Institute of Technology. And today, I will talk about copper alumina type oxide, ferroelectricity in copper alumina type oxide, but not alumina. So please remember that. And so this is my collaborators. And the outline of my talk is that first I will introduce the detail of the crystal structure of the copper alumina type oxide. Secondly, the polarization switching mechanism. And third, site preference of cation in copper alumina type oxide. And the main topic today is the chrome substitution in gallium ferrite films. And this gallium ferrite, sometimes gallium ferrite, people call gallium ferrite type, but same structure with copper alumina type. And also we have carried out the XS and the XMCD measurement for this material. And finally, we have observed the nanodomain structure by the STM. So first, I will explain the copper alumina structure. This is a well-known corundum structure. A corundum structure is made of the cross-packed layers of the oxygen. And inside the octahedral site, the cation can occupy. And the sequence of the cross-packed layers of the oxygen is AB. And in the case of the similar structure is gamma alumina type structure, defect spinel. And in the case of this, the cross-packed layer of oxygen sequence is ABC. And inside the tetrahedral site and octahedral site, cation can occupy like this. And also I will show you the copper alumina type structure. And this material, this is a mixture of the two material. And the oxygen cross-packed layer sequence is becoming ACAB. And also in this structure, you can recognize the corundum layer and the spinel layer, and alternatively stacking along the C direction of this material. And let's close look for this material. And there is 4 sites for the cations to occupy, A, B, C, D. And A is a tetrahedral site, and B, C, D are octahedral site. And this is a corundum layer and spinel layer and corundum layer. Spinel, corundum, spinel, and corundum layer. And if we look at cation arrangement inside the spinel layer, you can see the linear chain of the tetrahedral. And also you can see the linear chain of the octahedra of the B site cation. Also, you can see the if you look at the corundum layer, you can see the double zigzag chain of the octahedral chain like this. And this is complicated. So sometimes people say that this kappa-aluminum type has a gallium ferrite type or epsilon ferrite type structure, but all are the same. All three, these three have the same structure. And the most important point that the ferro along the C direction, and this material has polarization, electric polarization, and along the A direction, the magnetic easy access exists in this structure. And previously, by Professor Steffler, they have calculated the polarization switching mechanism for gallium ferrite with a kappa-aluminum structure. And the most important point is that when the electric field is applied, the change of the coordination change occurs along the C direction. For example, the original tetrahedron and octahedron turn into octahedron and tetrahedron. And this is the most important issue of this model. And this is based on the intermediate phase of PNNA. And if you use this intermediate phase, and the activation energy reaches up to 0.5 electron volt per formula unit. And maybe this is very large compared to the conventional type of ferroelectric material of barium titanate and lead titanate. And very large compared to that one. So we have re-examined the polarization switching mechanism by the calculation. And in this model, the intermediate phase of during the polarization switching, the PBCN. And the most important point is that in the spinel layer, you can see the coordination exchange between tetrahedra and octahedra. And originally, this site used to be a tetrahedron, but finally, this site turned to octahedron. And this is the A-axis view. And if we look at from the, along the B-axis, it is very easy to understand the mechanism. And in this model, when the electric field is applied, the corundum layer doesn't change their shape, but they shift each other like this. So after the shifting, shearing, the spinel layer changes their coordination from tetrahedra to octahedra, or from octahedra to tetrahedra. And I will just show you the result of the polarization of kappa-aluminum type structure for kappa-aluminum type alumina, and kappa-aluminum type iron oxide. And the polarization value is 21 to 26. And the most important point is that polarization switching energy is comparable to that of the perovskite, as I mentioned before. So in this material, this material is very complicated because cation position there are 4 cation positions, A, B, C, D. And the smaller cation, trivalent cation can be obtained, can be contained in this structure. And the largest ion is indium, and the smallest one is aluminum. And this material has site preference. And so we have. Today I will talk about gallium iron oxide. And we chose chromium substitution because according to the crystal field theory, the chromium cannot take coordination of 4. So maybe if we substitute chromium for gallium, maybe chromium is expected to take to be accommodated in the octahedral site. And according to the previous neutron diffraction data for the nanopowders, and the chromium ion can enter into C and D and C sites in the octahedral site in the corundum layer. And to prepare the single crystalline film, we have used the PLD technique. And all the films were deposited on the strontium titanate 111. This is just an explanation. And this is experimental data for the magnetization and polarization. And this is so this material shows ferroelectricity, ferrimagnetism and ferroelectricity. But today I will skip the magnetism of this material. And the polarization, let's look at the polarization of this material. This is a gallium ferrite, and partially substituted gallium ferrite, and 50% substituted gallium ferrite by chromium, and at room temperature. And these material shows a ferroelectricity like this, and also, but the leakage becoming large with the increase of the chromium content. So we have measured simultaneously. We have measured the PAND and the polarization by the PAND technique. So anyway, although the leakage current increases with the increase in chromium content, and these three materials show the ferroelectricity. And the valency of the coordination was checked by the XAS and the XMCD spectra. And this is the XMCD XAS spectra for this material. And this spectra shows the valency of the ion is 3. And also the XMCD spectra shows that this material, this is a spectra for the gallium ferrite. And this spectra shows that when the chromium is substituted for gallium, the peak for the tetrahedra increases. So it means that chromium, when the chromium is substituted for this material, the kappa ion in the octahedral site is expelled, and from the octahedral site, and ion can occupy the tetrahedral site. And this is a summary of the chromium substitution. And we can see that no change was observed in the polarization and the coercive field. So maybe, and let's compare with other system. And this is the previous work on the for this material. And these old material shows ferroelectricity, but the polarization value is small compared to the theoretical value. And this is about 10% of the theoretical value. And so to confirm the origin of the discrepancy between the theoretical value and the experimental value, we have checked by the STM observation. And this is a cross-sectional view of the by the STM. And so this is we can see in this system you can see the three kinds of domains and on the STO111 phase. And also this is a plan view of the thin film domains. And there we can observe the three kinds of domains with these directions. And also the average domain width is 12 nanometers. So the reason why this is just an estimation, but if the domain exists like this, with the three variants, and when the electric field is applied, the motion of these variants collide. So maybe this is the reason for the decrease in the experimental value of the polarization So now let's conclude my talk today. Is that we have carried out chrome substitution for this for gallium ferrite, and compared with and the ferroelectricity was observed in this material, and we have compared with the other system in the polarization, and also the similar smaller polarization value was observed in all the systems. So we are now estimating that this is due to the nano-domain structure. And we are now preparing to confirm this origin. We are now preparing the complete single crystalline film on single crystal, and to measure to check the theoretical value of the 20 to 25 microcoulomb per square centimeters. Thank you for attention.
Thank you very much, and I see there are a few questions.
Very nice talk. You had no time to discuss magnetic properties, but definitely you studied something. Can you comment magnetoelectric coupling in this system?
Because we should measure the ME effect, for example. But in the case of there is a domains inside. Exactly, we cannot determine the ME coupling value of this battery, but only the simple measurement was carried out and by the the sign of the I cannot sign of the
Thank you.
Any more? One more question. Yes. 1 second. There is one more question or comment.
I was just curious about the relative stability of this kappa phase as compared to the spinel and corundum. Is it stable in bulk, for instance, or what factors do stabilize it? Okay. 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 And what's the size of the nanoparticles? Okay, that's nice. Okay.
Okay. Let's thank the speaker again. And we come to the last talk of this session, which is the optical control of dielectric permittivity in wide gap aluminates, given by Dr. Nagai. Thank you.
Thank you, Chairperson. I'm Takayuki Nagai from Nagoya University in Japan. I'd like to talk about the optical control of the electric permittivity in wide gap aluminates. This is outline in my talk. First of all, optical tuning of physical properties has opened the way to develop the new photoelectronic technologies. For example, photoconduction is applied to photosensor, and photovoltaic is applied to solar cell. And in contrast, the dielectric materials are elemental components to design the electronic devices. So by combining them, we would be able to develop the photo-tunable dielectric materials, and it will probably shed light on the innovative photoelectronic devices. Photodielectric effects are the changes of dielectric permittivity induced by the photoirradiation. These effects have been reported so far in sulfide phosphate and contemporaelectric strontium titanate. Let me summarize the features of conventional photodielectric effects. This figure shows the frequency dependence of real part and the imaginary part of dielectric permittivity in strontium titanate. First, the dielectric permittivity is enhanced only in the low frequency region. Then, the divide type relaxation is observed at kilohertz region. Finally, the dielectric loss increases fatally. The origin of conventional photodielectric effect is caused by photoconduction. So the conventional photodielectric effects are unsuitable for practical applications. What can we do to find the materials with photodielectric effects not caused by photoconduction? Our approach for this issue is the generation of photoexcited carriers with significantly low mobility. If you can introduce deep in-gap states, the photoexcited electrons are localized. And if you can choose the materials with flat valence band maximum, the photoexcited holes are localized. Based on this, in this study, we focus the perovskite type oxide lanthanum aluminate. It has a wide band gap, low permittivity, and the valence band maximum composed of oxygen 2p orbitals. With these properties, we can introduce photoexcited electrons and holes with low mobility. So the localized photoexcited carriers probably work as dielectric displacements under the applied electric field. The purpose of our study is the development of materials with unconventional photodielectric effects. I will show in my talk the unconventional photodielectric effect, which was found in heterovalent zinc-substituted lanthanum aluminate. This slide shows the experimental procedure. We synthesize the polycrystalline sample by a solid-state reaction method and confirmed all samples to be in a single-phase state. Then, the dielectric permittivity is measured under the photoirradiation. Light sources used in the present study are LED and xenon spectral light source. The energy levels for various defects in lanthanum aluminate are calculated by first principles calculations under these conditions. In this slide, I will briefly introduce some problems in the measurement of physical properties under the photoirradiation. They are influences of local heating by the photoirradiation. In this work, we employ the non-contact infrared thermometer. This picture shows a homemade photodielectric measurement system using the infrared thermometer. With this system, the influence of local heating was successfully corrected in the present study. I will move on to the experimental results now. These figures show the frequency dependence of dielectric permittivity and tangent delta in zinc-substituted lanthanum aluminate and pure lanthanum aluminate, respectively. The black circles indicate the results for dark state, and red circles indicate the results under the photoirradiation. You can see in the low frequency region, the dielectric permittivity and tangent delta are remarkably enhanced due to photoirradiation. In addition, the dielectric relaxation is observed in the low frequency region. These are conventional photodielectric effects due to photoconduction. Here, please look at the high frequency region. You can find here the homogeneous enhancement of dielectric permittivity. This is the most important result in my talk. This behavior is different from the conventional photodielectric effect I mentioned at the introduction. In addition, the tangent delta is too low for conventional photodielectric effect. So this behavior is just the unconventional photodielectric effect. Furthermore, no enhancement of dielectric permittivity is observed in pure lanthanum aluminate. This result suggests that the heterovalent zinc substitution is important for the emergence of unconventional photodielectric effect. This figure shows the result for a switching measurement. The dielectric permittivity is measured at 1 MHz under a blinking LED. A vertical axis indicates the relative change of dielectric permittivity from the value in the dark state. When the LED is turned on, the dielectric permittivity increases immediately up to 7%. In contrast, when the LED is turned off, the dielectric permittivity decreases quickly from 7% to 2%. After that, the dielectric permittivity decays gradually toward to the initial value. These results suggest that there are at least 2 relaxation processes for photoexcited carriers with short and long relaxation times. This is excitation energy dependence of unconventional photodielectric effect at 1 MHz. The horizontal axis indicates excitation energy, and vertical axis indicates the relative change of dielectric permittivity. You can find the dielectric permittivity increases steeply at 3.5 electron volt. This energy is lower than the bandgap energy of lanthanum aluminate. This result indicates that the in-gap states are introduced by the heterovalent zinc substitution. Next, to clarify the origin of in-gap states, we investigated the energy levels for various defects in lanthanum aluminate by first principles calculations. In this figure, the result for only vacancies are shown. Among them, the in-gap states of oxygen vacancies are located at 3.55 electron volt above the valence band maximum. This energy is in good agreement with this value. So these results suggest that deep in-gap states stem from oxygen vacancies. I will briefly discuss an origin of unconventional photodielectric effect in zinc-substituted lanthanum aluminate. As shown by this schematic figure, the electrons and holes are generated by the photoirradiation. If the photoexcited electrons are trapped in oxygen vacancies, and if the photoexcited holes are localized in oxygen 2p orbitals, they are expected to form the photo-induced dipoles. So we suggest that the origin of unconventional photodielectric effect is the electric response of photo-induced dipoles. Finally, I will introduce the recent development of lanthanum aluminate-based photodielectric effect. We synthesize the lanthanum aluminate in nitrogen atmosphere to introduce the oxygen vacancies. This figure shows the frequency dependence of the electric permittivity and tangent delta in reduced lanthanum aluminate. The black circles indicate the results for dark state, and red circles indicate the results under the photoirradiation. You can find the dielectric permittivity is enhanced by 120% at 1 MHz due to photoirradiation. This rate of change is much higher than that in zinc-substituted lanthanum aluminate. Furthermore, the tangent delta is unchanged, especially in the high-frequency region. These results suggest that we can control the amount of unconventional photodielectric effect by changing way to introduce the oxygen vacancies. Let me summarize my talk here. The dielectric permittivity and the tangent delta are measured in zinc-substituted lanthanum aluminate and photoirradiation. The dielectric permittivity of zinc-substituted lanthanum aluminate in the high-frequency region is enhanced due to photoirradiation, with slight increase of tangent delta. We suggest that the unconventional photodielectric effect stems from the photo-induced dipoles in zinc-substituted lanthanum aluminate. The colossal unconventional photodielectric effect has been observed in lanthanum aluminate, which was synthesized in the reducing atmosphere. And we believe that the optical control of the electric permittivity opens a new route to develop the innovative photoelectronic devices. For example, laser-controlled touch displays may be realized. If you use it, you will be able to control the screen by photoirradiation, like science fiction films. If the photo-tunable dielectric materials are realized, they may bring science fiction closer to reality. The present study appeared in AIP Publishing newsletter. The present study is published in this paper. And recently, we have demonstrated the unconventional photodielectric effect in zinc-substituted barium aluminate. Please look at this paper if you'd like. Thank you for your attention.
Thank you very much for this nice talk. It's open to questions.
your low-frequency dielectric relaxation remind me Maxwell-Wagner contribution to permittivity. So cannot we explain all your effects by change of conductivity of your system with radiation and related appearance of Maxwell-Wagner polarization?
Okay. Thank you for your question.
Practically, you can distinguish it when you will measure permittivity on samples with different thickness. If you will have different permittivity in samples with different thickness, then it means that you change just conductivity and the depletion layer by electrodes will be all the time same, and then you will have change. You will have all the time same capacity with different thickness. It means different permittivity.
In this case, the energy of light source is 3.4 electron volt, and the band gap energy of lanthanum aluminate is 5.6 electron volt. The number of photoexcited carriers is extremely low. I think extremely low, and so in this case, conductivity. I think that conductivity is low, and the photoirradiation.
But you have always some oxygen vacancies, and then you can have some localized level in band gap. Yeah, I remind you, try to measure permittivity on samples with different thickness, and then you will have a direct proof whether is it defect or real effect.
Okay. Defect, number of defects. Sorry.
We can discuss it later.
I haven't checked yet the number of defects. I will try to check in future.
We can discuss it later.
Okay. Thank you very much.
Just short questions requiring a short answer.
Well, the short question is, have you measured the temperature dependence?
Temperature under photoirradiation?
Yes. For the entire effect.
I already measured. I have already measured. The enhancement of the electric permittivity disappear at about 700 Kelvin.
Yeah, that's not surprising, but have you measured low temperature at 60 K? There's an anomaly in lanthanum aluminium oxide, which is electronic, probably. Have you seen any effect there at 60 Kelvin?
Sorry,
have you measured at 60 Kelvin?
60 Kelvin?
60.
60. Okay. This one?
60 Kelvin.
Kelvin. Okay. Sorry. I have not measured at 60 Kelvin. Sorry.
And very short answer. Yes, no.
What is it? It's not yes, no, but what is the lifetime of these in-gap states? If they're long-lived, you might start exciting them into the conduction band and getting, again, photoexcited carriers.
This lifetime?
The lifetime of your states, you're in the gap. What is the lifetime? Do you know?
Okay. At present, I don't know about in-gap states in detail. Yeah, and lifetime is origin of lifetime is unknown.
Okay, no, you can discuss this after we take the photo. This again, short yes, no, nothing more.
There is a in case band titanate. If you reduce the oxygen, it makes 10 times more direct constant. It sometimes referred to the defect mode. Have you examined defect mode?
Say yes or no.
Yes. Sorry. Please discuss later.
Thank you very much. I would like to thank all speakers and turn it on.
Oh, okay. Everybody should just come up to the stage for the photo. So we'll just line up here in no particular order. Just watch your step coming up.
Yeah, I want to make sure that everything is fine because sometimes they have problems with the. Sorry.